Hello, this is Scott Dahman, Director of Business Development with PowerWorld Corporation. In this segment, we will demonstrate some of the key analysis features of PowerWorld Simulator and several of its most commonly used analysis tools.
The case I am using is a synthetic grid model on an ERCOT interconnection footprint. However, it is not an actual ERCOT model and contains only publicly available data. No critical energy infrastructure information is included. The accompanying notes on our website and the description in YouTube contain a link where you can download it. Let's start by examining some features of this geographically based one-line diagram. One-line diagrams are not required for analysis in PowerWorld Simulator, but they are useful visual aids that enable features such as color contouring and power flow animation. This diagram contains substations and transmission lines. All buses in the case are assigned to a substation, and the transmission lines are coded by color and line weight to indicate nominal voltage. Heavy lavender lines are the highest nominal voltage, followed by lighter lavender, and gray lines are the lowest voltage. We can navigate by zooming, panning, or recalling a saved view. For example, this view is centered on the southern tip of Texas. We can use screen layers to alter the level of detail that is shown, or use conditional zooming to show more detail when we're zoomed in, and to declutter when we're zoomed out. We can also jump to a neighboring substation by clicking on indicator arrows that show up at the edge of the display. Green flow arrows are sized in proportion to the real power flow in megawatts on each transmission line. This feature enables us to identify key transmission paths at a glance and understand how power gets from generation to load center. Pie charts indicate the flow on each line as a percentage of the line's thermal rating. They can dynamically size and change color as they get close to limits. We can play the animation and take a line out of service to see the impact on other lines. For example, this outage on the 500 kV grid causes flow to redistribute onto lower voltage lines, overloading this path between San Marcos and Austin. The base package of Simulator also includes sensitivity analysis calculations, such as power transfer distribution factors, or PTDF, and shift factors. With PTDF, we can select a buyer and seller and calculate how much of the resulting transfer will flow on each line, transformer, or interface in the power system. Suppose we are interested in the impact of interconnecting a wind farm in West Texas and selling the power to a group of data centers in the Houston area. We run the calculation and can view the PTDFs in tables, sorting if we wish from high to low. We can also visualize the transfer with a contour on the one-line diagram. Here, the color scale runs from green to yellow to red to pink, in a scheme similar to that used for precipitation intensity on weather radar maps. High PTDFs show where flow originates around the wind farm in the west. High voltage lines most directly along the path to Houston experience the most impact, but loop flow is also evident throughout the network. We can also change our flow arrows to reflect PTDFs. Here we've assigned red to PTDFs that run in the same direction as the underlying power flow, and black to those that provide relief to the underlying power flow. Simulator's Contingency Analysis tool, also part of the base package, can automatically process a set of contingencies and report limit violations. It has an option for linearized solutions to minimize runtime or full power flow solutions to maximize accuracy. Distributed computing is available as an add-on for processing massively large contingency sets. Results can be quickly sorted to identify contingencies, branches, interfaces, or buses that are most impacted. For example, these are the contingencies that cause the most limit violations. This contingency, the loss of a transformer at Alvin, causes other transformers in the bank to overload. These results show which lines and transformers are impacted by at least one contingency. I have sorted it by percentage overload, which reveals that these Magnolia transformers are loaded to 106% of their limit when the parallel transformer is lost. Here is a bus view online that shows the two transformers. We could then calculate shift factors for these transformers to determine which loads or generators have the greatest impact on their loading. This shows that the load at Magnolia has about a 32% shift factor, but other nearby loads are also very significant. Generators, on the other hand, have less than 1% impact on these transformers. We can also calculate composite shift factors over multiple elements. Here I have chosen contingency overloaded lines and transformers. The results provide individual shift factors for each overloaded element, as well as composite values that show which buses have the most impact across all lines and transformers in the set. Next, we might be interested in how much network capacity is available to deliver power from our proposed West Texas wind farm to data centers around Houston. Simulator's ATC, or Available Transfer Capability add-on, can show how much power can be transferred before a limit is reached on a line, transformer, or interface. Here we select a seller and a buyer, just as with the PTDF calculation. Each record in the results represents a pair of limiting element, a line, transformer, or interface, and a contingency under which that element is loaded to its limit. The transfer limit itself is the power in megawatts transferred from the seller to the buyer at which the corresponding limit is reached. Our first entry is actually negative, which indicates that the limiting interface is overloaded and that a transfer in the opposite direction from buyer to seller is necessary to relieve it. Subsequent entries let us know how much can be transferred if prior limits are resolved. We might also want to know how much power can be transferred until the power flow does not have a solution. This point, the static voltage stability limit, or nose point, can be found with the PV curve tool. Here, we specify a source and a sink, which are now set to match those that we used with the ATC tool. We have included 5 of the most severe contingencies from our earlier run. The results show us that the base case, with no contingencies allows a transfer of about 335 megawatts before the power flow fails. The contingencies cause a failure at lower transfers. We can plot the PV curves for each contingency near the point of interconnection for the proposed wind farm. Here we can see the base case curve with the highest transfer limit, as well as those with each of the contingencies. We might also be interested in the reactive power margin at the point of interconnection for the wind farm. Simulator's QV tool can trace a curve of bus voltages against additional reactive power load at that bus. We will first perform this analysis at the base case limit found by the PV curve tool, that is, at the maximum power transfer just before voltage collapse. We can see that the base case has just over 4 megavar of margin. That is, an additional load beyond 4 megavar would cause power flow convergence to fail. However, each of the contingencies requires additional reactive power to be supplied for the power flow to converge, between 76 and 115 megavar. For these contingencies, the QV curve does not cross the x-axis. We can also remove the transfer from the proposed wind farm by restoring the initial state from the PV curve tool. Now, if we recalculate the QV curves, we will see that we have additional margin for the base case and the contingencies. The worst contingency now gives us about 60 megavar of margin. Next, we will demonstrate Simulator's optimal power flow, or OPF. This allows us to simulate the dispatch in a wholesale power market using bids from generators. The OPF seeks a least cost dispatch subject to transmission constraints, which can be transmission line, transformer, or interface limits. After solving, we can examine the bus locational marginal prices, or LMPs. These may be resolved into energy, congestion, and loss components. We can also examine binding and unenforceable constraints and their associated shadow prices. In this display, we can sort the interfaces in descending shadow prices, and we see that 4 of them are binding. On the one-line diagram, we can apply a color contour to visualize areas of high and low LMPs. Here we see a few pockets of high prices around Houston. Finally, we will use Simulator's Transient Stability tool to simulate the simultaneous tripping of 2 large nuclear generators on the coast and the dynamic response of the power system. The generators are located here in the Wadsworth substation. They are each producing about 1,354 megawatts and account for about 4% of the online generation, making the double trip a significant event. The simulation begins with a 1-second flat start, followed by the simultaneous loss of both units. Once the simulation finishes, we have a few plots of results. Bus frequencies initially drop and oscillate as they approach a new steady state. Bus voltages also oscillate and return to a new steady state. This plot indicates the deviation in per unit from initial value for each bus. Hence, they are all zero to start, then most finish at slightly different values. Generator rotor angles also oscillate initially. Most return to a steady state, but a few seem to be growing undamped. We can also visualize the system response with a color contour. We can see how the disturbance spreads throughout the system. The frequency drops initially around the tripped units and then spreads westward. This system is small enough that it processes just a bit slower than real-time. But we could also save the contour images and make a real-time movie using software designed for that purpose. We'll end the demo with a movie created from these images.
There's additional detail on these features and much more in the free online training material on our website. I'll place a link in the description. On behalf of the team at PowerWorld, I thank you for your interest. Please reach out to us if you have any questions. Contact information is on the slide that follows.